Okay, let's unpack this a bit. Do you ever feel like the digital world, I mean, from how AI thinks to why these huge spreadsheets grind to a halt, it just feels like some kind of magic.
hmm
There's amazing power there, but figuring out how it actually works, that can feel pretty overwhelming.
It's fascinating, though, because a lot of that digital magic, you can actually break it down. It often boils down to understanding um, how numbers in tables, we call them matrices, how they change and relate to each other.
Exactly. And that's what we're doing today. Deep dive into those underlying structures,
Hmm.
the ones powering everything from AI to, analyzing data efficiently.
Right.
Our mission is to show how these complex systems that are often built from surprisingly simple parts. I'm
Mm.
going to give you a fresh perspective on it all.
Yeah, looking under the hood a bit.
We'll look at how AI learns, how data becomes this powerful map, and yeah, even why your Excel sheets get so sluggish.
Hmm.
All through this lens of numbers and how they transform. So let's start big. AI intelligence, especially these large language models, LLMs, it seems so huge, so complex. Where do we even start to understand how it's formed?
Well, maybe think of it like this. Picture a huge coral reef.
Okay.
It doesn't just pop up overnight, right? It grows over like thousands of years. Tiny little coral polyps adding one small piece at a time. AI's intelligence, especially in these language models, it forms in a very similar way.
So it's not this sudden thing. It's a gradual buildup, layer by layer.
Precisely. Think of the AI's total knowledge as this giant knowledge map. Experts call it a coefficient matrix.
Matrix, right.
When the AI is first born, so to speak, that map is basically blank. But then it learns something new, say Shakespeare wrote Hamlet.
Okay.
The whole map doesn't get redrawn. Instead, a tiny specific path, numerically speaking, is drawn or maybe strengthened between the idea of Shakespeare and Hamlet. It's a really small incremental update to that huge map. These numbers, the coefficients, they represent the strength of those connections.
Gotcha. Small incremental updates. And you mentioned these changes are recorded. What does that actually look like in the data?
So imagine you kept like a daily log for every tiny piece of learning the AI does.
Like a construction report.
Yeah, exactly. A daily construction report. Most of that report on any given day would be empty, just zeros. It might just say, okay, a new connection was made between Shakespeare and Hamlet with this specific weight.
Uh-huh.
Experts call that a sparse matrix. Sparse just means it's mostly zeros, only a few points have meaningful information.
And that's important, the sparseness.
Hugely important. It makes AI systems incredibly efficient. They don't waste time or memory on, blank information. They just focus on the actual connections. That's how these massive models can learn so much without becoming impossibly slow or gigantic.
Okay, so if it's all these tiny additions, these sparse updates, how does that lead to the really smart AI we see today?
It's actually quite elegant, really. Today's complex AI knowledge map, it's basically just the result of adding up all those daily construction reports, all those sparse matrices from the very beginning until now.
Just adding them all together.
Yeah. Each individual addition might seem tiny, insignificant even, but you add up billions, maybe trillions of them, and that cumulative effect creates the AI's vast knowledge. That summation of additions is what we technically call a linear combination.
Huh. So AI intelligence isn't some single magic talent. It's literally the grand total of countless tiny
Mm-hmm.
aha moments.
Terrible.
Well, it sounds a lot like how we learn, doesn't it? Our knowledge is built up over time from experiences. Language itself is like that.
It's a very powerful parallel. And this idea of complex behavior emerging from simple additive rules, that's one of the most fascinating things about AI. The scale makes the magic.
Right. Scale is key. Okay, that makes AI feel a bit less like a black box. But what about other complex digital things?
Yeah.
We're trying to understand AI's actual, thought process. Can we peek inside that?
Well, there's a useful technique here. Think about a master chef's amazing sauce.
Okay. Yeah.
Tastes incredible, right? Maybe a bit magical. But if you saw the recipe, first chop onions, then add wine, then simmer, the magic starts to make sense. It's just a combination of simple steps.
I see where you're going.
In the digital world, there's a technique called matrix decomposition that does exactly that. It unravels a complex result, or complex operation, into its basic recipe of simpler steps, simpler transformations.
And a matrix here is Well, it's more than just my Excel sheet, right?
It can be simple like an Excel sheet, just a table of numbers. But mathematically, matrices can represent really complex operations computers do, like moving graphics around on your screen or how an AI processes information. Each step, like scaling or rotating an image, that can be a matrix.
Okay, can you give us a concrete example? How does this decomposition actually work?
Sure. Let's say you have a final transformation matrix, call it X, that does something really complex to a graphic, maybe twists and scales it. Matrix decomposition is like a detective. It can figure out that this single complex matrix X is actually the result of doing several simpler things one after another. Maybe 3 simpler matrices, AAO, and A, applied in sequence.
So X is just A times AO?
Exactly. The complex result is built by multiplying these simpler intermediate steps together.
Yeah, those intermediate steps, A arrow, A. Can you break them down even more?
Absolutely. Often, each of those is itself a combination of even more basic things. Things like scaling, making it bigger or smaller, that's S, rotating it, R, and translating, just moving it, T.
So the super complex X is really just a long chain,
Like S arrows times arrows times arrows times arrows times arrows times arrows, or times arrow times arrow. You keep peeling back the layers until you get to the most fundamental actions.
wow, okay. That's pretty cool. So what does that decomposition idea tell us about how AI might be thinking?
Well, thinking bigger picture, when you ask an AI a question and get an answer, it's probably not just one single step inside its brain.
Right, it feels like more is happening.
It's likely a chain of complex phases, kind of like our final matrix X. Decomposition could theoretically help us map out that thinking process.
Into stages.
Yeah, maybe something like phase A arrows is understanding your question, breaking down the grammar. Phase arrows is accessing its knowledge, finding possible answers. And phase A's is picking the best info and putting it into natural language.
That makes it sound almost mechanical,
Mm-hmm.
analyzing, accessing, assembling. But what about when AI seems, intuitive or creative? Does decomposition cover that, or is that still the black box part?
That's a really good question. Even those seemingly intuitive leaps are fundamentally still complex combinations of these simpler mathematical operations. They're just happening at a scale and speed that's hard for us to really grasp. So decomposition helps understand the structure of the process. The black box feeling often comes from the sheer number of tiny factors involved and how they interact in unexpected ways, not necessarily from the basic math being different.
Okay, understanding structure is still huge. Speaking of complex systems, data, we're drowning in it, right?
Yeah.
Endless lists of customers, products, whatever. It's so hard to see the big picture.
Yeah, that's a key challenge. You ever stare at a long list, like customer names, and just feel lost? Like, what does this even mean?
Totally. It's like having a phone book but no map, just names and numbers.
Exactly. Data in lists is just points, isolated points.
So how do we get from just points to something useful, something meaningful?
The magic, again, is simple but powerful. You transform that list of points into a map of relationships.
A map. How?
Imagine a grid, like Excel again, customer names down the side, product names across the top. If customer A bought product Y, you just put a 1 or maybe the purchase amount in the cell where they intersect. Suddenly, it's not a flat list anymore. It's this map showing who bought what. It's a matrix again, but this one instantly shows you relationships. The real aha is realizing that turning lists into a matrix isn't just organizing, it's quantifying the relationships between things.
Okay, that feels like a game changer for anyone looking at data. What kind of insights does this map suddenly give you?
Well, it offers at least 3 huge shifts in how you see things.
Right.
1, you see the whole picture, no more endless scrolling. It's like being on an observation deck looking at a city. You see the whole system where things cluster together, the hot spots where it's quiet, maybe weird connections you'd never spot in a list.
Okay, seeing the whole system, what's 2?
2, you find hidden patterns. Studying this map, connections just jump out. You might see groups of customers, clusters, who buy similar stuff, or products that always get bought together, like finding constellations.
Like how Amazon or Netflix recommend things.
Exactly like that. This numerical mapping of connections is precisely how they do it. They see the patterns in the matrix and predict what else you might like based on your cluster.
Okay, whole picture, hidden patterns, and 3.
3, you can predict the next move. Once you understand these clusters and relationships, you can predict future actions better. Okay, a new customer fits this cluster, they'll probably like this product. It leads to smarter service, better suggestions, better strategy.
And I keep hearing about GPUs and TPUs making this stuff faster. How do they fit in? Graphics cards for data analysis.
Yeah, it sounds weird, but here's the key takeaway. GPUs and TPUs are changing how we even think about basic things like cross-tabulation.
Cross tabs, like in Excel pivot tables.
Exactly. Historically, that was seen as a step-by-step procedure for the computer's main brain, the CPU. Now we translate it into linear algebra.
Math again.
Right. We represent the operations as multiplying matrices or vectors.
Yeah.
And GPUs. They are phenomenal at doing matrix math really, really fast.
Why? What's special about them?
It's parallelism. Imagine building a wall. A CPU lays one brick at a time. A GPU is like having thousands of builders laying thousands of bricks all at the exact same moment.
So matrix multiplication can be broken down into lots of little calculations done simultaneously.
Precisely. GPUs excel at that parallel processing.
Okay, that makes sense. So if I have like a 3D cube of data, say age group by region by product category, and I want a 2D view, like age by region, summing up the products, how does that perspective shift work with a GPU?
Great example. That 3D cube is what we'd call a tensor, just a matrix with more dimensions.
Right.
To get your 2D view, age by region, you're basically telling the system to collapse the third dimension, the product category. You sum up all the product values for each age-region combination.
So for A0, region 0, I add up the values for product 0, product 1, product 2, and so on.
Exactly. T000 plus T001 plus 20001 plus T02. The GPU can do these summations across the dimension incredibly fast in parallel. It changes your thinking from, okay, loop through every single cell to, okay, just declare which dimension I want to collapse or transform.
That's a big shift. Powerful stuff for big data. But let's bring it back down to earth. That painfully slow Excel file, we've all been there. Why does that happen? What can we actually do about it? I swear, I wasted half an hour on one just last week.
Oh yeah, the dreaded heavy Excel file. It's a super common frustration. And often it's not really Excel's fault, it's how we're using it.
How so?
Excel gets slow when you have tons of formulas, especially complex ones like VLOOPs or lots of IF statements that link cells together. Every time one thing changes, Excel feels like it has to recalculate everything connected to it.
Wow, the constant recalculating.
Exactly. But Excel is lightning fast when it's just working with plain numbers sitting in cells, what we call immediate values, not formulas calculating those values.
So the formulas are the bottleneck.
Often, yes. It's that dynamic recalculation cycle that bogs it down.
Okay, so what's the magic trick? How do I make my slow file fast again?
It's surprisingly simple, even if it feels a bit weird at first. Select everything in your slow sheet, copy it,
Okay.
then open a new blank Excel file. And here's the key. Paste it as values only. There's usually a paste special option for this. Don't bring the formulas over, just the results.
Just the numbers.
Just the numbers, the immediate values. Then build your pivot tables or do your analysis on that new file. You'll likely find it's incredibly fast.
Because you broke the calculation chain.
Exactly. You've frozen the values.
Mm-hmm.
Excel now sees them as static data points, which it can handle super efficiently.
Yeah.
It's like you wouldn't use a Swiss Army knife for serious wood carving, right? You use a specialized chisel. Same idea. Use the tool appropriately.
That is a fantastic practical tip. Thank you. Okay, let's try and connect all these threads now. Numbers, changes, transformations. How does this apply more broadly? Like how information gets processed anywhere, maybe like in a factory?
Yeah, that's a good analogy. Think of a potato chip factory.
Okay, chips.
Raw potatoes go on one end onto a conveyor belt. They get washed, then sliced, then fried, then salted, then bagged. Each step transforms the potato.
Right, state change at each step.
Information processing is very similar. Your data, whether it's one customer record or a whole giant matrix, it moves through different digital processes and its state changes at each step. If you change one step, like swapping the fryer for a grill.
You get a different kind of chip at the end.
Exactly. Change a processing step, you change the data output.
So it's this continuous transformation pipeline. And that idea of small changes seems relevant again here too.
Definitely. It's fascinating how often big systems change through tiny increments. Think about zooming in on a web page. The matrix representing the pixels on your screen changes.
Mm-hmm.
But if you looked at the difference between the matrix before zooming and after zooming, most of the numbers in that difference matrix would be 0 or very close to 0. Only the pixels that actually change significantly would have large values.
Sparsity again. The change itself is sparse.
Precisely. Most of the information stays the same. Only a few key elements describe the actual transformation. This lets systems track and record changes very efficiently.
And these numerical changes, these transformations, You're saying they can tell us something deeper about the world, not just about computers.
I think so, yes. Consider this. Imagine drawing the number 0 on an Excel sheet, just using black and white cells, zeros and ones.
Okay, a pixelated 0.
Now apply a blur operation. Mathematically, this averages neighboring cells. The sharp edges get fuzzy. It's like finding harmony in data, smoothing out the harsh differences.
Blurring it out.
But now, try a different operation. Edge detection. This looks for sharp changes between neighbors. It highlights the boundaries, the essential differences, making the outline of the 0 super sharp.
Okay, blur smooths, edge detection sharpens.
Now, here's the interesting part. What if you apply the blur first, smoothing everything out, and then apply edge detection to the blurred image?
What happened?
You often reveal subtle boundaries and changes that were hidden inside the original sharp image, or maybe lost in the initial blur. It's like it shows that even when things look smooth and harmonious on the surface, there are still underlying differences, maybe fault lines or signs of change, waiting to be seen if you use the right lens.
That's quite profound. It's not just image processing, is it? It's a metaphor.
Exactly. It's a metaphor for analysis. Think about economic data. Blurring might show overall growth, but edge detection on that blurred data might reveal the subtle growing disparities between different groups, the hidden edges that could drive future shifts.
Wow. Okay, we have covered a lot of ground.
Yeah.
From AI learning like a coral reef, tiny piece by tiny piece,
The linear combination.
to breaking down complexity with matrix decomposition like a recipe,
Peeling back the layers.
turning data lists into powerful relationship maps supercharged by GPUs,
Seeing the whole picture.
and even getting that practical tip for speeding up Excel using immediate values.
Copy and paste as values. It works. And fundamentally, it all comes back to this core idea. The digital world might seem complex, but you can understand a lot by watching how numbers change and interact through these mathematical lenses, matrices, tensors, transformations.
Right. So for you listening, what does this all mean? It means you've got a new way to look at the digital systems you use every day. Next time you interact with an AI or wrestle with a big data set, remember the magic you're seeing. It's often the sum of countless, tiny, understandable steps. It's not really magic, it's just very clever math applied at scale.
Which leads to a final thought. If processing information is really about finding meaning in numbers, and if even in seemingly smooth, harmonious systems, those subtle edges can be detected, and maybe those edges even drive the future, like shifts in markets or opinions, then this raises an important question. What hidden small differences might you uncover in your own work or your own world if you only knew where and how to look for them?